In this part of chapter 4, we are going to discuss about forces of friction and then finally end the chapter 4. So before going into the forces of friction, I wanted to touch base on the apparent weight problem, which is a very interesting problem that we talk about if a person is sitting in an elevator and the elevator is at rest. We did a similar problem in the past, in the part 3 of this chapter. So if the elevator is at rest and we have a scale that is measuring what is the weight of this whole thing represents the scale basically, and there's a normal force acting on it and the weight is acting downwards. So the measurement when it is at rest is exactly equivalent to the weight of the person. So there is no acceleration. But when it's been observed that when the elevator goes up, there is the U weigh more. So that's why the needle has gone all the way here. And when the elevator comes down, you weigh lesser and the needle comes down. So we are going to talk about this problem in the lab during the lab time in detail, why it measures more while going up, why it measures while lesser going down, and why it is weightlessness. If the cable from the elevator is snapped, what happens in these scenarios. So we'll show them mathematically why the needle swings to zero, showing a weightlessness kind of feature. So basically we will start with the weight vector vertically downwards and the normal force vertically upwards, just as we said that we depict the forces upwards as positive, forces downwards as negative. Fn represents the apparent weight, which is the weight that is being observed on the scale, and mg is the true weight, and this m plus a is because we applied Newton's second law to this, which is net forces in fy direction is equivalent to m into a. You can also call it ay because we're talking about acceleration in y direction, and the net forces is actually made up of normal force and the weight, the sign plus for the upward and the negative for the downward. So this is how this setup plays, and if you are going upwards, you will have an additional m into a to it. If you are going downwards, we'll have mg minus ma, which makes the actual weight lesser than the measured weight. Next comes the frictional forces, which is the part that we are going to do in detail. Basically, friction is a force that is all around us all the time, and that opposes our motion between the surfaces in contact, but also allows us to move, which you have discovered if you have ever tried to walk on ice or sand on the beach. Frictional forces are needed in order to walk there. So while a common force, the behavior of friction is actually very complicated and is still not completely understood. We have to rely heavily on observations for whatever understanding we can gain. So, but still we can deal with it, its more elementary general characteristics, and understand the circumstances in which it behaves. So in a short way, we define friction as a force that opposes relative motion between the surfaces in contact. So on a microscopic scale, if we look at this picture, most surfaces are rough and have grooves. The exact details, although we don't know, but the force can be modeled in a simple way. So there are two different types of forces of friction. One is kinetic friction and one is static friction. Kinetic friction comes into play when an object is in motion, and static friction comes into play when an object is at rest. So this is a further explanation about the frictional force. If we have two different surfaces sliding on each other, and we are trying to show that at a microscopic level they have grooves and all, and because and interlocking happens, because of which the object experiences an opposing force. So this opposing force is the frictional force. And when two surfaces are not sliding across one another, the friction is called static friction. So no matter how big the force you are applying in this direction, the object seems to not move. So that means there is something that is holding it back. Check the magnitude of this vector and this vector. At this time they are equal because the object is still not moving. So that means our force applied is still equivalent to force of friction, static friction. We call it static friction. And second, he increased the force again, but it's still not moving. The static friction is still opposing the motion, and still the applied force is equivalent to force of friction. But after trying different types of applied forces, we succeeded in moving, because now you see this vector is greater than the maximum static friction. That means it's that F force of friction when it has actually given up. It's the maximum static friction force, means it's the maximum value of frictional force beyond which it cannot hold off anymore. It has to give in to the applied force and it starts moving. So we have static friction is directly proportional to the normal force. That's what is the formula. The more the normal force, the more the force of friction. This is the mathematical concept. If you remove the proportionality, we have a constant which we call coefficient of static friction, force of static friction. We generally write it with a small case to differentiate it from so many other forces that we know of. We say it is less than or equal to. When it is equal to, it is that maximum static frictional force where it gives in and the object starts to move. So that's what I meant by this letter, which is called mu, is a Greek letter and is read as mu. It's not a u, and we call this as coefficient of static friction. If you divide this equation by Fn, if I divide this equation on both sides by Fn, I can define the mu s. The mu s is therefore equivalent to force of static friction if it's maximum divided by normal force. Since both are forces, means the unit is Newton and Newton for both of them, the coefficient of static friction has no units. Because it's a coefficient, it's the ratio of similar type of quantities, the units cancel out. Note that the magnitude of the frictional force has no relationship with area. It simply depends on the normal force. All right, so it does not depend on the area of the contact surfaces. Static friction opposes the impending relative motion between two objects. Kinetic friction opposes the relative sliding. So when an object is in motion, it tries to oppose the motion, but the formula is then given by force of kinetic friction is equal to coefficient of kinetic friction multiplied by the normal force. Whether it is static friction or whether it is kinetic friction, both are dependent on normal force. All right, heavier the mass, the more is going to be the force of friction. Lighter an object, the lesser is going to be the force of friction, because if they are in contact with the surface, their weight will be, their normal force will be lesser. Is this mu k? Again, mu k represents coefficient of kinetic friction. Mathematically, it is equivalent to, it's the ratio of force of kinetic friction over normal force. Again, it has no units because it's a ratio. Ratios do not have units because it's not Newton over Newton and they cancel. It becomes a number simply. Different surfaces have different types of coefficients of static friction and kinetic friction. For example, the table in your book shows, for example, for wood, the static friction is 0.4 and the kinetic friction is 0.2. So on and so forth. So whenever I give a problem in the exam, I will always give you the values for it. So now how to solve problems using kinetic friction and static friction. So for example, this person is on the sled and when it's moving, but it's being slowed down by a certain force, and that force, because it was already in motion, that force in the opposite direction is going to be kinetic friction. So this represents the free body diagram for it will be normal force in the upward direction. Remember, in the free body diagram, we don't draw the whole person, we draw a dot for it, and mg in the downward direction. Force of friction, small k, is shown this way, but since it was already it was given a push, there is no applied force in this direction continued. It just has a force of friction, and there is acceleration because the velocity is changing over here. The sled comes to a halt because kinetic frictional forces opposites its motion and causes the sled to slow down. So what if we are given certain values for this person who is on the sled? What if we are given the initial velocity, which is 4.0 meters per second, and since it's coming to rest, the final velocity in the x direction is 0. So can I find the kinetic frictional force? Of course, our Fk is equivalent to mu k into Fn. The normal force here, because the person is not going up in the y direction, the net forces in the y direction are going to be 0 because there is no acceleration in y direction. So we can say that m into ay is, we apply Newton's second law, but since there is no acceleration in y direction, ay is equivalent to 0. The net forces will be 0. That means Fn minus mg is equivalent to 0, which means Fn is equal to mg. So I can easily find the normal force. We substitute for mu k, which was given. We know the mass of the person and the sled together is 40 kgs. We know the value of g as 9.8, and when we multiply all these quantities, we are able to find the force of kinetic friction equal to 20 newtons. So it's interesting to note the problems for how to solve the problems for force of friction. The static frictional force keeps on increasing as the applied force is increased until it reaches a certain maximum value, and that is why we have static force of friction less than equivalent to mu sfn. When it reaches its maximum value, it becomes equal to mu sfn, but to reach that maximum value, you have to keep on increasing the applied force. And f of k, force of friction when it is moving in the is given by mu k. Kinetic friction represents this because the object is now moving already. So we can understand this phenomena more if we can just work on few problems and then go ahead and work in the lab, and then also work on tutorials and dynamic study modules in order to get this very important concept cleared. So the problem is from your textbook, and if the coefficient of kinetic friction between a 22 kg crate and the floor is 0.30, so that means you have been provided as the mass and the mu k. What horizontal force is required to move the crate at a steady speed? When we say steady speed, remember there are always hidden answers, hidden things given. When we say steady speed, we know that it's saying that acceleration in the x direction is 0. What is the horizontal force required if mu k is 0? So there are two scenarios for this one. We'll go ahead and solve first for the part A. So part A, we draw the free body diagram first. Okay, if you want, you can first draw a diagram to understand what is happening. Oh, okay, there will be normal force in the upward direction, there will be gravitational force, which is the weight in the downward direction, there's force of friction, he's saying, and there is there an applied force? Of course there must be some applied force, or the force of push or pull that the object is experiencing at because of which it is moving. So this is just step one, trying to understand. Just as I said, you should break it into steps, several steps. Step one should be FBD. If you do not follow a certain pattern and randomly do it, you'll get them wrong. So instead of drawing a box, we draw a dot and we write normal force in the upward direction. The size of these two vectors is same because the object is not going in the y direction. So we are said if the coefficient of kinetic friction between the floor is this, what horizontal force is required if mu k is 0? So a free body diagram is shown. The crate does not accelerate vertically, so we can always show. So there is force of friction, kinetic friction this way, and there is applied force, we can say FA or FP, which is pull. So either way it's fine as long as you know. Now we want to find out what is happening in the y direction. Net force in the y direction is 0 because it doesn't have any acceleration that way. So Fn must be equal to F of g. So let's take a look at what is happening in x direction. So we can say net forces in x direction is equivalent to mass times acceleration. But the crate does not accelerate as it is said in the x direction also. So ax, it's going at a steady speed. So therefore, what are the forces in the x direction? We have Fp, which is positive. We are following the xy axis rule. All the forces towards the right positive, all the forces downwards negative, all the forces towards left negative. So Fp minus of force of friction, which is in the negative x direction, is equivalent to 0. Therefore, force of push is equivalent to force of friction. So that this will give us the value of the force of friction, and we know the formula of force of kinetic friction is mu k times Fn. But we earlier found out Fn is equivalent to mg because it's balanced in this side. So we get mu k times mg. I want you to understand that whenever we have to find normal force, we always rely on y direction equation for normal force, because normal force is a part of forces acting in the y direction, so you cannot ignore them. So the force of pull or push is equivalent to mu k times Fn over here, and mu k times Fn is equivalent to mg, the weight, because it's directly proportional to it. Mu k was given as 0.30, no units with coefficient, and then where mass is 22 kgs, and the acceleration due to gravity is 9.80 meters per second square, and you end up getting the force in the horizontal direction as 65 newtons. So you should always start doing the problem first yourself and then see. But then there was another question. It was asking what horizontal force is required if mu k is 0. Well, if mu k is 0, there won't be any horizontal force required. If the coefficient of kinetic friction is 0, the horizontal force required is 0. So if mu k is equal to 0, you can check in the formula over here. We have mu k, so Fp is equivalent to 0. Since there is no friction to counteract, of course it would take a force to start the crate moving, but once it was moving, there's no horizontal force necessary to maintain the motion. Think about the ice puck, that first it's given a hit, and once it's given a hit, you're not continuing that force. It goes on all by itself to the other end, and on ice there is very less force of friction, so almost frictionless, and there is no opposing force, so it goes forward. Then there is another problem from your textbook that we are working on. There is a force of 35 newtons which is required to start a 6.0 kg box moving across a horizontal concrete floor. You have to find out the coefficient of static friction. Now this time the box is not moving. You have to find out when it is going to start moving. What is that force? If the 35 Newton force continues, the box accelerates at 0.60 meters per second square. What is the coefficient of kinetic friction? So there are two parts to this problem. In the first part, you are finding force of static friction, coefficient of static friction, mu of s. And in the second part, you are finding mu k. So first, in order to understand the problem, we'll have to use the support from the free body diagram. Before drawing the free body diagram, let's draw our usual sketch to understand what is happening. So force of friction is on this side, it's either static if it's not moving, or it is kinetic when it is moving. So depending on part A or B, we will switch the Fk and Fs's. And the normal force acts normal to the surface, and it is written as Fn. And vertically downwards is the weight. And then there is this applied force, or you can say F of P. Step number 1, now I'll go, step number 2 I should say. Step 1 is to understand the problem, read the problem, list out the variables which you're going to do, this is the mass we have. Then we are going to draw a free body diagram for it. Fn and Fg are same length, and if the force of static friction, if the object is not moving, the pulling force and the static frictional force will be equal. But if the object starts sliding, then the force of static friction ceases and we get kinetic friction. Okay. So for part A, to start the box moving, the pulling force must just overcome the force of static friction. So that means Fs must be equal to mu s F of n, and Fn, as you must be seeing, is equal to, your Fn is it's the net force in the y direction is 0 because there is no acceleration in y direction, and the net force is made up of Fn minus Fg equivalent to 0, which is Fn is equivalent to F of g, that is equivalent to mg. So we know, we go to the x direction now, and we can find the mu s. Then we have m into g. Our job is to find coefficient of static friction. We have been provided, we still have to write the net force equation in the x direction, where the net force in the x direction is m into a, but is the object accelerating? So since the box is still in the static friction mode and it's not still moving, we can say for the maximum static frictional force max equivalent to 0, because we are talking about part A where force of friction is static. So we get fp minus f of s equivalent to 0, which means the push or pull is equivalent to static frictional force, but fs is equivalent to mu s mg, and this is fp. So fp is 35 newtons. From here I can calculate the coefficient of static friction, fp over mg. When I substitute the values, fp is 35, m is given as 6.0 and 9.8, I end up getting coefficient of static friction, which will have no units because both are in newtons, the denominator and numerator, and a 0.60 is the value for the coefficient of static friction. So that was part A. For part B, where it says that if 35 Newton force continues, the box now is accelerating. If you're continuing to use the same force, but now the box is accelerating, so my net force in the x direction now changes the equation, and I'll have ax, the acceleration, because in part B it's giving the acceleration, but I still get to write the equation this way. Instead of writing static friction, I will write kinetic friction because the object is now moving, and I have to find coefficient of we have to find mu k, coefficient of kinetic friction. So fp is still 35, but I want to rearrange the equation. Fp minus mu k fn, because the force of friction still stays the same, the formula is still same, except we replace mu s by mu k, which is m into ax, and rearranging the terms we will get fp minus m into ax is equivalent to mu k times fn, where fn is equivalent to m into g, because it doesn't change, fn is still m into g. And then substitute the values. So we have 35 minus m, which is 6, multiplied by 0.60, whole divided by m, which is 6. So we divide both sides by mg because I want to keep mu k alone. M is 6, g is 9.8, and that is equivalent to mu k. When you use this number in the calculator, you end up getting mu k as 0.53. Again, mu k will not have units. It is a ratio between two forces, and it is always found that mu k, the coefficient of kinetic friction, is always less than mu s. Mu s is always more, because it takes more force to move an object from its state of rest than keep an object in motion, which is kinetic friction. So the last but one problem, suppose you are standing on a train accelerating at 0.20 gram, sorry, not the grams, 0.20 g, which means 0.20 multiplied by 9.8. Okay, so what minimum coefficient of static friction must exist between your feet and the floor if you are not to slide? So that means you're not going to slide, but what is that minimum force? So you are standing on a train which is accelerating with an acceleration equivalent to this value, and you have normal force between the train floor and your feet, and mg is acting downwards. So same scenario, and a free body diagram will be simply Fn in the upward direction and mg in the downward direction, but the train is accelerating at a 0.20 g, so that acceleration is this way, because that's the force of friction is between the floor. So force of kinetic friction or static friction, if it's not moving, there will be force of static friction. If it's moving, there will be kinetic friction. So what minimum coefficient of static friction must exist between your feet and the floor if you are not to slide? Not to slide means that you will not slide until your force of friction is greater than ma. Okay, so in other words, force of friction must be greater than or equal to mass times acceleration. There's no pulling force here, and force of friction, or we can say static force of friction, F of S, which is mu s mg, should be greater than or equal to A, and we get mu s greater than equal to A over g. But we know that that acceleration is equivalent to, mu s is equivalent to 0.20 times g over g. This gives me the coefficient of static friction as 0.20, and this is the coefficient of static friction that I need in order to keep my feet firmly on the ground so that I will not slide. All right, so with this we will end chapter 4, and we will meet in the lab and work on few more problems to get this concept clear.